Okay. So, welcome, Tristan. Tristan McLoughlin is going to tell us about non-planar n equals 4 supersymmetric angles from integrability to quantum chaos. So I think this is our first one with chaos in the title, chaos in the title. So thanks very much, Tristan, for agreeing to give.
No problem. Although I see, does everyone see this meeting is being recorded? Notice over the slides.
Not for us, no.
Okay, good. So I want to talk about some work that was done last year and is ongoing, and it was done together with Raul Pereira, who was a postdoc at Trinity, and Anna Spearing, who is a PhD student at Trinity just for a little while longer, and she's going off to MBI in Copenhagen. And we're going to be interested in, generally speaking, what I am interested in is the properties of non-abelian gauge theories in 4 dimensions. And of course, this is a huge topic and there's too much, so I'm going to focus down a little bit, and I'm mainly going to talk about the supersymmetric conformal field theories. So if you have maximal supersymmetry in 4 dimensions, so that's n equals 4, the theory is finite, so there's no running of the coupling, the beta function is 0, and the theory is exactly conformal. So in this theory, I'm going to, it has some, obviously, it shares some features of QCD. Obviously, the conformality is the one that it significantly doesn't. But it is a sort of a theory of non-abelian gauge fields, and so the field content includes a mu, the gauge field. In addition, though, it also contains scalar fields. So it contains 6 real scalar fields. So here, A is an index that runs from 1 to 4. There's a SU4 R symmetry, sort of flavor symmetry or internal symmetry of the theory. These indices here are anti-symmetric, so there's 6 real scalar fields. And in some part, I'm going to focus on the behavior of those scalar fields, though much of what I will say generalizes to including the effects of the dynamic of the gauge field. The theory is also supersymmetric, so indeed it also contains the fermionic, the supersymmetric partners of these bosonic fields. All of these fields are in the adjoint representation of the gauge group, and I'm going to consider the gauge group being SUN. So all of my fields are going to be sort of n by n matrices. And we're going to consider different values of n, and in some sense, the behavior of the theory for different values of n is largely what we're going to be interested in. This theory is, of course, incredibly well studied. One of the reasons that's been so well studied is it's been conjectured to be dual to type 2b superstring theory on ADS5 times S5, and therefore somehow is meant to encode all the mysteries of quantum gravity and so on. Now, I'm not really going to have anything to say about that, but in some sense, of course, that provides some of the motivation for why I'm looking at this, and also in principle would provide sort of an alternative viewpoint on some of the things I'm going to say, though that will all be basically left implicit. One other thing is that this theory is sort of, you can think of it as a single case of a 2-parameter family of theories, which are also conformal. And in this case, they have reduced supersymmetry. So these are n equals 1 marginal deformations of this theory. So I'm obviously talking about a very special theory, but it's not unique in some sense. So a lot of what I will say does generalize to some degree to these other, it does generalize to these other theories, these marginal, the deformed theories. So it's not just a unique case, although it still is very special. Okay. So the thing that we're going to be interested in looking at, or one of the basic objects that you might be interested in computing in a conformal field theory, are 2-point functions. So you take some basis of operators, and the operators that I'm going to be interested in, they're going to be gauge invariant. And so therefore, they're one class of such operators is traces of products of fields. So you evaluate the fields at some point, you take products of them, and then you take the trace so that the resulting composite operator is gauge invariant. So generically, I'm labeling these operators O alpha, and then you might want to calculate the 2-point function. And if you do perturbation theory, and again, nearly everything what I'm going to say is going to be a statement in perturbation theory, and because n equals 4 is conformal, you can think of the coupling being weak, and so perturbation theory is reliable. And so the 2-point function has this form here. So for a generic operator, so delta 0 is the engineering dimension, it's the sort of scaling dimension of this operator O alpha. There's some tree level part, so basically just doing Wick contractions of the fields in your operators. So there's some tree level part which corresponds to this matrix S alpha beta. And then of course there's quantum corrections. And the quantum corrections, you have to introduce a cutoff, a regularization scale, and this, this introduces anomalous dimensions. So the scaling dimension of the operators gets corrections, and there's another corresponding matrix. There's a mixing matrix of the different operators, and this is this matrix here, T alpha beta. And the basic building blocks for calculating such 2-point functions is so that the form of the correlator is fixed by conformal invariance, and so really the only thing you want to find are essentially the eigenvalues of this matrix T alpha beta, or slightly more precisely, I want to calculate the eigenvalues of the dilatation operator, the generator of scaling transformations. So the generator of scaling transformations has the tree level part, the engineering dimension, and then it has this loop correction. And the loop correction is just given by this expression here in terms of the data you would extract from doing perturbative calculations. So this D2 here is the eigenvalues of D2 give you the one loop anomalous dimensions. And so this is,
excuse me, so the delta 0 is corrected, right, by these
exactly. So the delta 0,
that's just okay.
Yeah, exactly. It's corrected by the eigenvalues of this D. Yeah. Okay. And so the delta 0, you'll see in a second, it's just kind of, it's just going to go along for the ride. And the thing I'm really interested in is the eigenvalues of D2. And of course, in principle, I'm also interested in all of the other corrections as well, and I can say a little bit about that. But what we've really looked at is just the one loop correction first. Very good. Okay, so that's the thing I'm interested in. I'm interested in calculating the corrections to these dimensions, the anomalous dimensions. And then, as I said, the field is the theory is quite complicated, but I'm going to sort of focus a little bit just for the purposes of this talk, and also because we didn't look at the most general thing. We're going to look at operators made from, so previously I said there's 6 real scalar fields. So I'm going to pick 2 complex combinations of those scalar fields, and then I'm going to look at I'm calling that X and Z, and then I look at operators made just out of those fields. And so the operators that I would look at are operators like the ones here. So I can take arbitrary products, I can take traces, and then I can take products of those traces, right? So I can have multi-trace operators, and the full set of operators, a basis of operators, is formed from all operators of this form here. L1, L2, L3 are just sort of arbitrary, that's a product of Z's. And it's been known for quite some number of time, I don't know, 20 years or whatever, what the one loop dilatation operator is in acting. So like if I, these operators, one thing about them is they don't mix with any of the other operators, so they form a nice little closed sector. So I can consider the action of the dilatation operator just on these operators, and they mix amongst each other, and that's the mixing problem that I'm going to be interested in. And the dilatation operator in this sector is given by this formula here. So this is the one loop piece. So the G here is my coupling constant. N is the rank of the gauge group. Essentially what it does is that, so like acting on such an operator here, the Z hat and the X hat, these are sort of functional derivatives. They take derivatives of these fields, and then they insert sort of combinations of these fields back in. Right? So this is sort of how it acts, and these are just the regular commutators, the normal ordering thing. So these functional derivatives don't act on the fields inside the dilatation operator. Okay, so this is what it looks like. As I say, this is just something you extract from doing a perturbative calculation. Well, one thing you can see is that it's going to like take traces and split them apart. It's going to take traces and join them together. It's going to take x's and z's, and it's going to exchange them in a given trace. So it takes all of these operators and mixes them all together.
Sorry, Tristan, can I just ask, just to make sure I understand,
Yeah.
Is your X O alpha and the Z O beta in that? Is that what you mean?
No, sorry. So O alpha, so this here would be an example of O alpha, the whole thing. And then O beta, well, so here's a concrete example. So here's an example of length 4 with what we call 2 impurities. So it's operators made out of 2 z's and 2 x's. So this list here of these 4 operators, this would be O1, O2, O3, O4. Right? So this is the, and you can see that there's different orderings of the x's and z's within a given trace, and there's given as I say, you can also have multi-trace operators. So I can have
And you're assuming that n is large enough that that the traces are independent.
Very good, exactly. So this will be important, right? So I'm going to assume that n is larger than the length. Now later, or I can also take n to be smaller than the length, and then as you say, then you have to take into account there's trace relations, and we did do that. So you can let n be larger than L. It's just slightly simpler for the moment to take n to be finite but larger than L. Yeah, but we can give that up. But actually, in this talk, I won't discuss those trace identities, but you can do that. Okay. So yeah, so indeed, so for example, that's what I'm going to do. Actually, I'm going to so delta 0 in this case here would just be 4. So all of these operators all have the same delta 0, and then you can calculate the one loop mixing matrix. That's what I've written here, and you can calculate the eigenvalues, and that's what I've labeled by delta. I probably should call it delta 2. So these are the one loop corrections to the anomalous dimensions. And one thing you see is that first of all, I get zeros. So there are protected operators, and this is in some sense characteristic of the supersymmetry. So there's going to be operators that don't get any corrections, but there are non-vanishing. There are operators with non-vanishing corrections. This here is the Kanishi operator for those of you who've looked at these sort of things. Okay. So slightly more, I don't know, schematically, you can sort of take this one loop dilatation operator and sort of visualize how it acts by using this spin chain picture. And so what you can do is you can take this trace operator here, and you can sort of visualize or map this to sort of a spin chain state where you take the z's to be spin up and the x's to be spin down, and then this is some closed spin, like closed periodic spin chain. And the dilatation operator can be sort of broken into 3 parts. There's a part where it takes, for example, one of these closed spin chains and gives you back another closed spin chain, but with the spins sort of shifted around. There's a part which takes a closed spin chain and splits it into 2 parts and also moves the spins around. And there's a part that will sort of take 2 spin chains and join them together. This part here, this part is leading in n. So if you expand in n, the splitting and joining parts are sub-leading in this parameter n, if you keep n arbitrary and do the calculation. And indeed, this leading part, if you focus on it, is known to map to a spin chain Hamiltonian, and it just maps to the XXX Heisenberg spin chain Hamiltonian, which of course is known to be integrable. So the spectrum of one loop anomalous dimensions in the limit of large n is just the spectrum of the XXX spin chain. It's known to be integrable, can be solved by the Bethe ansatz. And this has led to sort of a large amount of work. And this then does generalize it. It's known that the full one loop Hamiltonian spin gets mapped to a supersymmetric spin chain Hamiltonian. It's known to be integrable. It's known to be integrable to all orders. So you can go to 2 loops, 3 loops. It's sort of the whole thing is integrable. It's has been solved by TBA, and so there's a whole long story where people have really looked into the planar spectrum, and in some sense you can consider that a solved problem. There's this quantum spectral curve method for determining anomalous dimensions in the planar limit that is very, very efficient for computing the anomalous dimensions at finite values of the coupling for arbitrary states. But what I'm going to be interested in is sort of understanding a little bit about what happens when you work at finite n, and also what happens when you kind of go from infinite, or from very, very large n to finite n. So this is the obviously integrability quantum chaos kind of thing. Okay, so just to be a little bit, again, I do apologize. I think for some of you, a lot of things I will say will be very, very simple. Yeah, well, what can some of these things were new for me. This is not necessarily the area I was working in. So
never hurts to hear things we already know.
That's exactly. I think that's the other thing. It's true. People always enjoy hearing things that they know. And then if they know them better than the speaker, they can join in and tell him that he's a fool. Okay. In any case, one of the standard things is that that at large n, whereas I say the theory is integrable, if you look at the spectrum of anomalous dimensions, the levels will cross, while at finite n we expect the levels to repel. Now, because I'm working just at one loop, I can't really think of the coupling as a parameter, which is when people make this statement, that's sort of what they mean. You know, for me, the parameter just sits out in front. There's no dependence on the parameter. So what we do is we as I said, it's not just this maximally supersymmetric theory. We can also look at these marginal deformations. And so in particular, I'm going to be interested in what is called the Bethe deformed theory. So this is really, it has the same operators, it has the same field content. The interactions of the theory are just slightly different. They're modified. There's an extra parameter. In particular, you can go ahead and compute the one loop dilatation operator, and that's something that we did. In some sense, this was probably already kind of known in the literature, but we, I don't know, dotted the I's and crossed the T's. And so the one loop dilatation operator has this form here. You can see that it has a piece that's very much like the n equals 4 theory, where it just has these commutators of the fields. The one slight difference is that these commutators are twisted commutators, so they now involve this parameter, which I maybe should write down. So something like this commutator beta just looks like x to the I beta minus e to the minus I beta zx. So it's some sort of twisted commutator depending on this parameter. And then it also has a double trace term that in principle is subleading in n. So you actually kind of don't see it if you're looking at the planar theory, except when you're looking at length 2 operators, where there's a sort of a combination of traces which cancels this n. But for the most, so in the planar limit, this double trace term is not important, but at finite n, it certainly is. But the other thing is that, and what's relevant for us is that yeah, the theory now depends on the theory and the dimensions depend on this parameter beta. So again, we just look at the same.
Tristan, you define it, and at the level of the dilation operator, could you also define the Bethe deformed theory on the level of the Lagrangian?
Yeah, no, sorry, exactly. So I mean, so the Lagrangian is essentially that of n equals 4. If you the n equals 4 Lagrangian has a quartic interaction for the scalars, which I'm probably not going to be able to write down. that looks something like this, I guess. And the Bethe deformed theory, you just deform the commutators depending on the R charges of the scalar fields. And actually there's a double trace term that you have to add to the Lagrangian to preserve conformal invariance. And there's similar coupling, sort of slight deformations of the coupling for the fermions. Actually, in fact, if I use n=1 superfields, you have this. So I guess I didn't actually quite catch who the question was from, but in any case, if you write it in terms of n=1 superfields, writing down the deformation is essentially trivial. You have this cubic superpotential, and you just introduce the e to the I beta in two of the terms.
It was from Werner.
Ah, okay. Well, then Werner will know about the n=1, the n=1 superfield formalism. In any case, in that case, it's very, very straightforward. You just modify the superpotential.
Yeah. In the beginning, you said you have two parameters for deformations with n=1 supersymmetry. Is that one of them? Or?
Exactly. So that's one of them. And the other one is where. So again, in this superfield formalism. So these are the two Lee Strassler, the Lee Strassler deformations. You have another one that. Sorry. So this is a n=1 superfield, and the other one is this cube. Oh, sorry. So in this case, you have three chiral superfields, and the other marginal deformation looks like this. This one does not preserve integrability in the planar limit, and so yeah, but this one does. The Bethe deformation does preserve integrability in the planar limit. So that's
and presumably that's a cube on the last one as well.
And that's a cube on the last one. Sorry. Yes.
Thanks.
Yeah. So we don't actually consider this one. Well, yeah, I can say a little bit maybe at the very end. Yeah, maybe I'll reserve some things at the end. Okay. So indeed, just to go back to this level crossing thing, I can ask what the spectrum of the theory looks like as a function of this parameter. So again, if I focus on operators which are length 6 and have 3 impurities, so I mean something like x, 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 z, z, z. So all operators, and including multi-trace operators and so on, of this form. It's again trivial to compute the matrix and to look at how the anomalous dimensions behave as a function of beta, and then you get these sort of nice curves. In particular, so here this is for n being well, essentially infinite, and this is for n being 6. And what you can see, of course, is that at very large n, you get these crossings of the spectrum, while at finite n, you don't. Sometimes it looks like they come very, very close, but actually, if you zoom in, you'll see that they're still separated by 1/n. So this here would be 1/36, which on this scale is very small, but if you can zoom in. You see that they don't. So this makes sense. So that at infinite n in the planar limit, effectively, you get this level crossing, while at finite n you get level repulsion. There is one operator, this one here. Oops, that didn't work. This one here, which is crossing the other operators. Even at finite n, there's one operator that just sort of plows through the other guys. It doesn't care about their existence in some sense. And this one operator has a charge, so that there are some sort of global symmetries. So in particular, here I'm considering L is equal to 3. L is equal to 6, M is equal to 3. So I'm sort of at half filling from sort of the spin chain point of view. And at half filling, there's an additional symmetry, where if I exchange Z and X, and I reverse the order of all my traces, this combined transformation leaves the dilatation operator, the one loop dilatation operator, invariant. And so there's a symmetry, and that one operator that's sort of not correlated with the other ones is the only operator that has negative charge with respect to that symmetry. And this is the usual thing where when you want to see level repulsion, you have to desymmetrize, right? So you have to remove any sort of global symmetries that are, or sort of, yeah, other symmetries that are around. And so that's what's happening here. The crossings that occur, these generally occur at beta over pi being some rational number. And this actually makes sense. The theory is known to have, it becomes essentially just an orbifold of the n equals 4 theory at those points where there's sort of enhanced symmetries and sort of, yeah, that makes sense. This behavior as a function of n is characteristic of the transition from integrable to chaotic systems, that level crossing occurs in integrable systems, level repulsion occurs in generic quantum chaotic systems. And so this led us to suspect that that's what's going on here. And so we wanted to investigate, well, okay, is there some characterization of quantum chaos in the spectrum at finite n? And one standard way of doing that is by analyzing the statistical properties of the spectrum of anomalous dimensions. One thing that's kind of nice is that, so here I'm talking about the spectrum of the dilatation operator. So I'm really considering the theory on the plane. You can make a conformal transformation where you map the plane to R times S3, and then the dilatation operator maps to the Hamiltonian of the theory on R times S3. And so in that sense, you can also think of that we're computing the spectrum of these composite operators. And this I also find, I mean, somewhat nice in that obviously a lot of this, not that I'm an expert, but the origin where people looked into the properties of the spectrum goes back to looking at the spectrum of large nuclei, and they were looking at the energy spectrum of these, and it was in looking at this that they, that Wigner and was led to make many of the early sort of observations about this. And so here we have sort of like a toy model where we're calculating. So we can think of these composite operators as something like nuclei, and we can think of the dilatation operator as essentially the analog of the Hamiltonian. So we have some reason for expecting to see the same behavior. Now, of course, at the same time, this is non-trivial. You might think, well, n equals 4 super Yang-Mills is a very, very special theory. We already know it's special in the planar limit, and so maybe it doesn't share sort of any of these sort of generic properties that we would expect to find in, say, a theory like QCD. Okay, so that's why we were interested in looking at this, and we saw that there were some hints, and so we went about analyzing it a little. So in order to do this, this, as I say, is kind of standard. So what we do is we and that's why I'm going to use the language of energies. So I sort of stop using the language of dimensions and I talk about energies. But I'm always interested. Well, yeah, I'm talking about the one loop anomalous dimensions. So we take our spectrum, we order it E1 through En. We compute the spacings between the energies. So I define these SIs, which are just the distance between neighboring energies. And then we can ask, what is the probability of finding a given given spacing between S and S plus ds, and this defines for us the probability distribution. And we can, so this is, we're going to do this for our spectrum, and we have some basic expectations just by sort of, if you take sort of a range of energies, and if you just dropped them down sort of randomly in some sense, if you assume that the energies are uncorrelated, and if you assume that the average spacing is just 1, then you would find that the probability distribution, just by doing a small little calculation, is described by the Poisson distribution. And so it goes like e to the minus s. Alternatively, if we assume that the probability, so if I have some energy level, if I assume that the probability of finding the next energy level is at e plus s, sorry, the probability of finding the next energy level at e plus s is proportional to the distance away from that energy. So if I'm very close to that energy, I expect the probability to be very small, so because s is essentially 0. So that's sort of what we saw on this level repulsion. Then you can show that the probability distribution of the spacings is given by the Wigner-Dyson distribution. So here it has this sort of linear behavior for small s, and then it falls off like a Gaussian for large s. So it's sort of, first of all, it goes to 0, unlike the Poisson. So the Poisson goes to 1, and then sort of falls off sort of relatively slowly, whereas the Wigner-Dyson goes to 0, increases linearly, and then falls off like a Gaussian. And as I say, it was Wigner, in some sense, based on some remarks by Bohr, going back to earlier models, was sort of led to propose that this distribution described the level spacing of large nuclei.
This depends upon symmetry class, though, right?
Yeah, no, absolutely. It very much does. Yeah. So here I've described the GOE.
The GOE, yeah.
Yeah, and that's what we're going to find. So yeah, yeah.
So is it obvious why you have that symmetry in your system?
So you probably know you get GOE if you have essentially the like a time reversal symmetry.
Yeah.
And there are discrete symmetries which are presumably the analog of time reversal symmetry in this, and that's why you get GOE. Yeah.
Okay, thank you.
Right. So very good. So yeah, in order to do this analysis, so one thing we need to do is we need to sort of desymmetrize our spectrum. So we already saw that when we looked at the sort of the length 6 operators, that the yeah, that there are some sort of at half filling, there's this discrete symmetry which sort of builds in accidental degeneracies, and we want to remove those. So we work in sectors that have no sort of obvious symmetry between them. The other thing is, as I sort of briefly alluded to here, this universality that we see that's sort of common from quantum chaos is not at the level of the spectrum. So it really is to do with the fluctuations in the spectrum. So if you look at for example, and I'll mention this a little bit later, but if you look at like random matrix theory, you get this semicircular distribution, whereas if you look at, say, spin chain, you get something that looks more like a Lorentzian curve. So the overall distribution of energy levels is not shared. So what we want to do is we want to sort of remove the average part of the spectrum. So remove the average part of the spectral density so that the mean spacing is 1, and then we look at the fluctuations about this local mean. So this goes by the name of unfolding. I'm not really going to discuss it. I'm happy to discuss it like later, or if people want to, and ask us how we did it. But from what I understand, this is a standard thing in the literature. You always do this, and we used basically standard methods. We used a bunch of different methods. The results don't actually depend don't depend very much on how you do these things. Okay, but that's the first thing. So we remove the overall behavior, the behavior of the dependence of the spectrum on the energy, and then we just look at fluctuations around this average behavior. And then we look at the sort of classes of operators that have fixed length and fixed, so as I said, impurity numbers. So so they have a total number of x's and z's is L, and the number of x's is M. There is some supersymmetry so we remove the protected states. So the protected states will just have anomalous dimension equal to 0. So we just throw those away, and we look at the non-protected ones. And then we also avoid this half filling where there's sort of an additional symmetry. And in the case of the Bethe deformed theory, that's enough. So if you restrict the Hilbert space to that sector, there are no sort of global symmetries. And then we can look at we unfold the spectrum, and we can look at the distribution. And what we find is essentially plotted here. So here we're looking at L being 16 and M being 7. And here N is, and I actually forget the exact number. Well, no, actually here N is infinite.
So remind me what L and M were.
Yeah, sorry. So again, so I'm looking at operators like of this form here. The total number of scalar fields in my operator is L.
Okay.
And the number of X's is M. So that's and as I say, we're also looking in principle at multi-trace operators, and sort of, not all operators are single trace, they're multi-trace and whatnot. And in both of these cases, so here N is essentially infinite, or N is infinite, and so there's no trace identities. Here we look at N being 16. So again, there's no, the N is big enough that the largest single trace operator, there's no trace identities. We don't have to take those into account here. So, and so one thing, maybe let me say, yeah, so the number of operators of this form, and again, I think I've forgotten exactly, but it's roughly about 8,000. So if you look at all the different multi-trace operators, with all the different possible ways of distributing the X's and the Z's, taking into account the cyclicity of the traces and so on, you find that there's about 8,000 of these operators. And then you act on these 8,000 operators with your dilatation operator, and you get a 8,000 by 8,000 matrix. And then you just calculate the eigenvalues of that matrix for some particular, so everything is done numerically. So we pick some particular value of beta. So here, and again, I probably can't remember exactly, but I think beta is around 0.7. So we pick some particular value of beta. And that's the only parameter. And then we just end up with some numerical 8,000 by 8,000 matrix. Just calculate its eigenvalues. It's not, that runs quite quickly. And then we do this unfolding. So we calculate the spectral density. We remove an overall average part, and then we just look at the fluctuations around that average part, and we order them, we calculate the different distance between them, we bin them, and then we plot we normalize it, and then we get these two graphs here. So in the limit where n is infinite, so one thing that does happen when n is equal to infinite is that these different multi-trace sectors decouple from each other, right? So as I said, this splitting of a single trace into a double trace and so on, this is something that happens at finite n, but does not happen at infinite n. So the different sectors decouple from each other. So all the single trace operators, they mix with each other, but they don't mix with the double trace. So we have to look at each sector separately. And then within that sector, so in, say, for example, the sector of single trace operators, you find this Poisson distribution, or so the red dots are the numerical data, the blue curve is the Poisson curve, and yeah, I mean, you can see that it visually looks quite close. We did make some efforts at sort of characterizing, trying to fit to curves and so on like that. But I think just looking at it, it's relatively good. And then we did the same thing for finite values of n. So for n is equal to 16. And now the mixing between the different single trace and multi-trace operators is all mixed up. And you can see that you get this this Wigner-Dyson distribution. And again, the red dots are the numerical data. The blue curve is the Wigner surmise. And you can see, again, it's a reasonably good fit. We did, again, sort of fit to different curves. You can look at this so-called Brody distribution, which sort of interpolates between Wigner and Poisson, and you can check how close it is. And then also you can look at the other ensembles. So there are other ensembles, and you can, this one fits best with the GOE. I'm not giving the actual numbers for those fits, but yeah. Again, I think it looks just visually is reasonably clear. They're in the paper, there's some more details. Okay. So that was for the deformed theory. You can
just out of curiosity, you said you had roughly an 8,000 by 8,000 matrix.
Yeah.
There. You could look at the largest eigenvalue there and check if it's Tracy Widom.
Yeah, that's true.
That would
we
be
did not do that.
Okay.
Yeah. No, sorry, hold on. Let me go back. This would be to do with the overall spectral density, right? You mean is the distribution of eigenvalues given by at the edge, is it given by Tracy Widom? Right. This doesn't have to do with the fluctuations. And in this case, yeah, it's not going to be, sorry. So the distribution looks more like a spin chain distribution than it looks like random matrix. The fluctuations are given by random matrix, but the overall distribution is more like a spin chain.
Okay.
Yeah. I think that's, I mean, sorry, what I said is true. The connection to your question is right. So so that's, roughly speaking, that's the story. That is the appearance of quantum chaos in the spectrum. We then generalized this. We pushed it a little bit more. So let me just mention a couple of the things. So one, as I said, we looked at the thing I just showed you was for this marginally deformed theory. You might ask, well, does it also hold in the undeformed theory, or maybe that theory is too special? But you can go to the n=4. In this case, what happens is that there's additional symmetries. There's an SU2 symmetry. So you have to desymmetrize. You have to basically perform additional desymmetrization. There's a global symmetry of the dilatation operator in SU2. So you have to remove all the SU2 descendants. What this means is that for a given L and M, your Hilbert space is smaller, so the statistics are not quite so good. I'm not sure. I think here the Hilbert space even for length 17 goes down to about 3,000. I'd have to look up the number. But you could, so the fit is not quite as good. But we're limited by sort of the length just by computer power. These things start to take it's actually not calculating the eigenvalues, it's computing the action of the dilatation operator on the states. That becomes a little bit, it takes a couple of days. But I think nonetheless, again, it's certainly the best fit is to Wigner-Dyson GOE, and again, it's reasonably good. You can also ask what happens if we include higher loop corrections to the dilatation operator. So for example, the 2 loop corrections to the dilatation operator are known. This is a little bit tricky now. I don't want to, well, maybe if people ask me questions, but roughly speaking, what we did was that you take the 2 loop dilatation operator and the 1 loop, you pick some particular value of the coupling. So here's a range of different couplings. So G being varying from 0.1 to 1. So this means that the relative size of the 1 loop and 2 loop are kind of going from the 2 loop being very small to basically being comparable. And you calculate the spectrum of this combined operator, and you can see that at finite values of n, you still get this Wigner-Dyson distribution. So that adding in the 2 loop dilatation operator doesn't seem to remove this generic quantum chaotic behavior. Not that maybe you would expect it to, but it doesn't. You can also look at operators that are a little bit more kind of gauge theory type operators. So we can look at operators which say involve one of the scalar fields and covariant derivatives. So I can take one of the covariant derivatives, pick a light cone direction. So plus here, I pick light cone coordinates. D plus is a covariant derivative involving the gauge field along one of those directions. And I can form scalar operators by inserting various different powers of these covariant derivatives. And again, actually, this is known at one loop to be integrable in the planar limit, where it's described by an SL2 spin chain, a non-compact spin chain. But again, if you include the finite n corrections in this SL2 sector, the spectrum again is well described by Wigner-Dyson. So it seems to be relatively generic. Now, as I said, we haven't looked at like all loops in all sectors, but within this sort of limited case, every time we extend it, we basically find sort of that the behavior is the same. In some ways, of course, this is what you would expect, right? It's the integrable behavior that's kind of special. This quantum chaotic behavior is generic. So, you know, it's not perhaps not so surprising, but still, nonetheless, I think it's interesting that we find it in what is sort of a very special theory. Yeah, I'll come back to that a little bit. Okay, so these spectral statistics, these fluctuations are sort of known to be very, very universal, and in particular, are shared by random matrix theory. And so, if we consider, again, from the questions, people know this, but if we consider an ensemble of real symmetric matrices with entries h, j, k, being random variables, and the random variables having a joint probability distribution given by this Gaussian function. This is known as the Gaussian orthogonal ensemble, random matrix theory, and the spectrum of the eigenvalues of the level spacing is known to be well approximated by this Wigner-Dyson distribution. So you can compute it efficiently numerically, so it's not exactly Wigner-Dyson, but it's very, 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 very close. There are other ensembles, so unitary and symplectic, which result in slightly different distributions. One of the main things is that they have this the ramp up or whatever, the behavior near zero for the different distributions sort of is different, and it's particular. You can see for the spectrum of n equals 4, it's linear, which is characteristic of the orthogonal ensemble. And the different ensembles correspond to different symmetries, and the GOE describes systems with rotational and time reversal symmetry. And you can see that if I look at the dilatation operator, there are discrete symmetries that are the analog of, for example, a time reversal symmetry for a spin chain. And so it's presumably that's producing this GOE ensemble rather than the alternatives. Now, one of the things is that, so this is this famous conjecture by BGS, that quantum chaotic systems have spectra whose fluctuations are described by random matrix theory. And so this then makes predictions for correlations, like for further correlations of energy levels, right? So we can, you know, I don't know, the logic depends on how you want to go, but one way you could say we're now convinced, or we now have a conjecture that the spectrum of this theory is described by random matrix theory, and so we can, you know, make predictions. So one further sort of observable of the spectrum is the so-called spectral rigidity, and this is measured by looking at the cumulative level number. So this is the staircase function, right? So the EIs are just the different energies. So if I have some spectrum, now here the epsilon i's, by this I mean the unfolded spectrum. So everything I'm going to talk about is the unfolded spectrum. So these are the unfolded energy levels. I make this staircase function for my my spectrum. And one quantity that measures the spectral rigidity is this Dyson meta-statistic. Yeah, I'm obviously going to run way over time, so let me. I won't. I mean, it's given by this quantity here. It's related to the two-level correlation function of the spectrum, and correspondingly can be related to something called the spectral form factor. If you're familiar with these things, you'll have seen this. But it gives us basically another probe of the correlation between energy levels. If we look at the Bethe deformed theory with with L is equal to 17, M is equal to 8, and N is equal to 17. So again, there's no trace identities. The blue curve is the prediction from random matrix theory, and the red dots are again the numerical data. You can see that essentially for a large range of parameters, so L here is this quantity that entered into the definition of the Dyson method statistic. It's very good, and then it's only for very, very large values of L, for very well separated energy levels, that this starts to break down. Okay, so that's one other one that you can ask is that random matrix theory also makes predictions not just for the spectrum but for the eigenstates of the Hamiltonian. In particular, if we choose some generic basis A, such that the eigenstates are given by some linear combination of this basis, then we can define the information entropy in the usual way. And this sort of gives a measure of how delocalized a given state is, in our case, the energy eigenstates, over some specified basis. And again, the prediction from random matrix theory is that the information entropy is given, sort of goes like the log. So here, m, little m, is the dimension of your Hilbert space. And so for chaotic systems, the entropy goes like the log of the dimension of the Hilbert space. And the various characteristics are, the actual coefficients are fixed by the ensemble, slightly different for different ensembles. So we can compute this for the gauge theory. This is the results that you find. So let me just briefly mention. So here I'm measuring the ratio of the entanglement entropy for the eigenstates of the dilatation operator with respect to, sort of normalized by the GOE prediction. So 1 would be the GOE prediction. The yellow dots here are the results that you find for n being like 10 to the 12, so essentially very, very, very large. And one thing you see about them is that, well, first of all, the entropy is relatively lower. So the states are a little bit more localized. And the other thing which is characteristic is that the entropy is not particularly a function of the energy. So here on the x-axis, I've labeled the states by their unfolded energy. So this is sort of the anomalous dimension being 0, and then this is the anomalous dimension being the largest value, and I spread them out so that the mean density is 1. And you can kind of see it as I go through the energy spectrum, the entropy sort of just bounces around, right? So it's very dispersed. The blue curve at the top, this is n is equals to 16. So this is the finite value of n. So this is the quantum chaotic system. And you can see that the entropy is generally higher. It's quite close to the GOE prediction. And more than that, the entropy is sort of a function of the energy. It's close to a straight line. It does dip down a little bit towards the edges of the spectrum. This is also characteristic of many systems, again, and chaotic spin chains. It's only near the middle of the spectrum that you find genuinely GOE values. In fact, here, the fact that the entropy is quite large near sort of one of the boundaries is slightly more surprising. But this sort of suggests, as I say, that the entropy is a function. So you're sort of reaching some thermodynamic state. So like microcanonical. Does this look like a microcanonical ensemble? That's one way of thinking about it. One thing I mentioned, this going back to Denjo's question, is that you certainly can take n to be smaller than L. And then what happens is that, some, so if n is equal to 2, and if I have some length 4 operator, this is going to be given by some product of length 2 ones. And so what happens is that the number of operators you have becomes smaller, right? So now, so like, for example, you lose this length 4 trace, and so you have fewer and fewer states. So the dimension of the Hilbert space sort of shrinks a little bit. In fact, if you do go all the way down to n is equal to 2, you can only make your sort of your operators out of these length 2 things, and actually the dynamics becomes actually very, very simple. In fact, even at n equals to 2, there's a very slightly surprising thing where the one loop anomalous dimensions become solvable. It becomes trivial to diagonalize the Hamiltonian. Now, I don't know whether that's some feature of just 1 and 2 loops where we checked it, but there's something very special that happens in this sector. I don't know what happens if you look at the full theory, but more generally, you can certainly take into account these reductions, and it doesn't really. So one thing, as I say, because you have a smaller Hilbert space, the statistics are slightly poorer. So here, this is n is equal to 4 for the same L is equal to 16 states. The statistics is poorer, so that's why there's sort of fewer dots. But it looks, I don't know, just as chaotic in some sense, which is not unsurprising. In fact, it looks a little bit flatter. It looks almost, I mean, it's yeah, okay. I don't maybe want to get over my skis characterizing this too much, but this is what the entropy looks like. Essentially, all the states are delocalized, and they're sort of they're very delocalized, and they're all delocalized. Okay. Okay. So what we have, just to take away from what we've looked at, we have the conjecture that n equals 4 super Young-Mills, and the Bethe deformed theory is chaotic at finite n, and is described by GOE random matrix theory. And it makes sense to conjecture that that would be true to all orders in the coupling. We certainly haven't proved that, but that would be the obvious conjecture. If we included a theta term, so if we included in the action, then this would break time reversal, and we might expect that the statistics would become GUE. And there was a comment to this effect in a paper a few years ago by Kotler et al. And that's where this comes from. But for us, we don't include this theta term, and so we expect the statistics to be GOE. There's additional evidence that this is true from looking at the dimensions of operators who scale like n squared. So these are so-called giant gravitons in the UN theory, where these authors here used a sort of a different basis of states, not this multi-trace basis, but the so-called restricted Schur polynomial basis. And they showed that in this large n limit, in the limit, looking at the class of these giant gravitons, that there was sort of fast scrambling is how they characterized it. So this sort of characteristic of quantum chaotic systems. The random matrix theory predicts observables are thermalized in the sense that their expectation values agree with the microcanonical results. So we expect that at finite n, the spectrum of energies is described by the microcanonical results. That's sort of the follow-on conjecture. And we also, this makes sense from the point of view that at large lambda, so if I go to a very large coupling, a 't Hooft coupling, and I look at operators whose dimensions go like n squared, these should be dual to black holes. And so we would expect to find some thermal behavior. Now we're very far from large lambda, but that matches up, at least to some degree. And then the other takeaway thing is that this n equals 4 theory, even though it's very special, at finite n is very generic. So we might actually hope that we can use n equals 4 to still extract interesting things about generic quantum field theories. So that's good. On the other side, the bad thing is that finite n might be very, very hard, because it's going to be maybe just as hard as any other theory. Now I'm out of time, but let me just take 5 or 10 minutes or 5 minutes just to give an idea about how we might use what we might do. So this is the second half of my talk, but I promise not to go over it all. The reason
okay, we're relaxed about time.
No, exactly, and you did say that's why I felt comfortable taking just a few, but nonetheless, I'm not going to go crazy. I don't want to say too much about this. But what I do want to say is that the planar theory is integrable, so we can calculate the planar spectrum. So then we can ask, can we use the integrability of the planar limit to organize the non-planar contributions? And the idea would be that we could try some sort of large n expansion. So this is still not going to get us finite n results. So this bit is slightly different than what I was talking before, in that I don't have a method for generating finite n results. But I do want to say that you can use the planar integrability to organize the 1/n expansion and to get relatively nice expressions. At least, okay, so that's the claim, and we have some small evidence that this is true. So the idea is very sort of is very straightforward. If you recall, I had this picture of the dilatation operator as sort of this splitting and joining of spin chains, and if I do just perturbation theory, I can just treat the 1/n splitting and joining corrections as a perturbation of my planar theory, and I just do quantum mechanical perturbation theory. And the leading 1/n squared correction is just going to be found by using the textbook, quantum mechanical perturbation theory formula, right? So the building blocks from this are the matrix elements of my my perturbations, so my H plus and H minus, and then these are the planar energies. The planar energies we know. So of course, then you have to do a sum over all of those energies, and doing the sum over the solutions of, say, the Bethe equations is a non-trivial problem. So there's lots to be done, but nonetheless, at least in principle, you know these things. And so we can organize this calculation of at least the 1/n correction as just a sum over matrix elements of these H plus and H minus. So the thing is, can we use the planar integrability to get nice expressions for what I've labeled here as V plus and V minus? And that's one thing you can do. And the reason that it's doable is, as I say, it's this map to the integrable spin chain. So I briefly mentioned before, in the planar limit, the different trace sectors decouple, so I can just focus on single trace operators. I can map such operators to spin chains, the spin ups and spin downs. The energy eigenstates are given by the Bethe ansatz, and so I can write down the energy eigenstates. They're just characterized by some momenta. The wave functions are known. They're given in terms of what's called the S matrix. So this is the one loop S matrix. Actually, this is just the Heisenberg spin chain again, as I said, although the generalization to the full theory to all loops is known. And here I've written it in terms of what's called a rapidity variable, but it doesn't matter too much. So the point, though, is that the eigenstates of the dilatation operator in the planar limit are known and can be written down in terms of relatively compact forms. So then what we have to do is we have to just compute the overlaps of the dilatation operator between single trace states and, for example, double trace states. So the double trace states here are, again, characterized by two Bethe states. So each one is a solution, is characterized by some set of momenta that satisfy the Bethe equations. And then this is my single trace state. And the point is that you can write down, so this formula here, of course, is using lots of compact notation, so it's obviously cheating. Every equation is simple when you don't write down the details. But the building blocks, so this object here and this object here, these are off-shell scalar products. And the scalar products of Bethe states, including where one of the states is off-shell, so this is to say the momenta don't satisfy the Bethe equations, is known to have relatively compact expressions. So this is due to Slavnov. There's the Slavnov, so-called Slavnov determinant formula for these objects. So these things can be written in sort of, again, relatively nice forms. This sort of notation here I've introduced, these are just phases that you have to, so these are just objects that are written in terms of the S matrix. They sort of tell you how the various different excitations, what happens when they go around a loop, they pick up a phase as they move past each other excitation. And these objects here just encode that phase in terms of the known S matrix. And then there's another sort of overall phase. So the point though is that these matrix elements can be written in terms of known objects from integrable systems. Okay, now, yeah, and these are the formulas, so I'm not gonna write them down. They're also related to structure constant calculations, but I'm not gonna go through that. Moreover, you can use these things to efficiently compute anomalous dimensions that include the non-planar, the 1/n² corrections to the anomalous dimensions. Again, it's useful to go to this deformed theory, carrying out the sum over these intermediate states. So as I say, I have this picture here where I'm taking my object and splitting it into two pairs, and I have to sum over all possible Bethe states, all possible eigenstates of the Hamiltonian. This is non-trivial, but at least in a certain case, we were able to do it. And you can produce sort of closed expressions. This is just an answer. Again, it doesn't matter too much. It's just to say that the method can actually be used to compute something. Okay, so all of that is just to say you can use the integrability of the planar theory to at least in part simplify the non-planar contribution, at least at one loop. We hope to go to higher loops. In the calculation of the spectrum, the planar spectrum, you certainly could go to all loops. The carrying out the sum over intermediate states is one of the most complicated parts. There is something known the quench action approach, which might be useful for doing this. In particular, if we look at states that have large numbers of excitations, so large numbers of x's. And then there's some suggestions that that these objects that we've computed can be so-called bootstrapped. As I say, for the spectrum, you could write down essentially axioms that allow you to write down functional equations that determine the spectrum to all orders. And this has been generalized into something called hexagons and octagons, which I haven't had time to discuss. And there's some suggestion that the objects that we wrote down have similar properties. And so therefore, you might hope that you can generalize this to all orders, but there's lots and lots to be done before you get there. Okay, that's all I wanted to say. Thank you very much.
Well, thank you very much, Tristan, for a very interesting talk. And then the floor is open to questions. Anyone want to kick off?
I just wanted to ask, when you're doing these perturbations off integrable systems, are you doing it? I mean, I guess you can do it, and maybe you are doing it. I didn't quite understand. For spin chains, right? You can just perturb spin chains, and then maybe try to understand the spectrum or in that context.
No, absolutely. So yeah, and I do apologize for going too fast. I think it's very clear, but in some sense, that's exactly what we're doing. We are perturbing off spin chains. Yeah. But just let me say, it's a slightly funny perturbation in that the perturbation splits spin chains apart and joins spin chains together. So when you include these corrections, you have to change your Hilbert space to the space not just of say, so the planar theory is closed spin chains, and then you can have like tensor products of such closed spin chains, and when these perturbations mix single closed spin chains with tensor products of spin chains, essentially, a closed spin chain is a single trace operator, and so then if I have products of traces, that's like the product of two spin chains, and the perturbation mixes these. So I've never actually seen in, say, the spin chain literature, and I mean, I don't know experimentally how you would do this, but I've never seen anyone consider this type of perturbation.
No, but you could just consider, you could just put in a next to nearest neighbor or a third nearest neighbor interaction, right? And that breaks your integrability.
No, exactly. So that's the thing. So so there is, right, so those type of perturbations do actually also occur, and I was going to say, so we've also looked at those types of perturbations.
Those should be easier to work with, right?
No, and they are easier to work with, absolutely.
Yeah,
So from our point of view, we really wanted these 1/n corrections. That's what's interesting to us, and so like there's a physics reason for looking at that. It's so, but you're right, they're strange. They so you can look at the other ones, and actually let me just say one thing. There is good physics reasons for looking at the type of, say, non-nearest neighbor interactions that you're talking about, that break integrability. And actually there's special classes of them that occur that sort of are motivated from gauge. So the generic non-nearest neighbor interactions, as you say, just give you quantum chaos, Wigner-Dysons, like this, one of this. But there's special classes that are motivated from, from this gauge theory picture. And they're non-nearest neighbor interaction, but they break integrability, but they don't break it a lot. And so there's somehow, so the quantum chaos in the context of this gauge theory really comes when you look at the finite n corrections. If you look at the spin chains that arise, at least the ones that we've looked at, they break integrability, but only a little bit. I feel like I haven't been very clear, but you certainly can look at those two, and they are interesting. But these finite n corrections are particularly of interest for what we were doing, and therefore and they do. It means lots of the standard things just don't quite fit right, and therefore I have been looking at some of the more standard.
Thank you very much. Unfortunately, I have to go.
Thank you. Other questions? I'm curious to know about the n equals the smallest n's that you looked at to n equals 2.
Yeah.
You could have looked at n equals 3 as well. I mean, I think n equals 2, 3, 4, and possibly some of those ones, the algebra of trace relations is completely known.
Okay.
So it might be interesting to look at n equals 3 as well, that being the next simplest one, to see if something also happens there.
So we looked at for a given value of L, we worked at all the trace relations for all values of
I mean, there's a basis that you can use, which you can express all of the matrices in terms of products of a particular small number of elements.
Yeah. No, exactly. That's quite right. So.
And again, you can do that rather easily for n equals 3, and even n equals 4. It's not more difficult, I would say, than n equals 2.
Okay. So one thing that we found is that, as I say, when we go to n is equal to 2, the quantum chaos disappears. In fact, the system becomes entirely solvable. So n equals to 2 was very special. N equals to 4, we did still see quantum chaos. N is equal to 3, I'm trying to remember now. I don't think we could, algebraically. So for n is equal to 2, we could just write down like a very simple closed formula for the the one loop anomalous dimensions. I don't think we could do it for n is equal to 3. Maybe we just didn't work hard enough. But n equals to 4 was genuinely quantum chaotic. That's what I showed you there. So that's kind of interesting, because then if there really is such a set of relations, maybe it's like analytically tractable, but still quantum chaotic, which would be
yeah, even n equals 4 is analytically tractable. I mean, the relations are written down. I believe the simplest set are written in terms of not simple traces, but traces made from partitions, as in Schur functions type.
Yeah, no, exactly. This Schur basis seems very promising, and so yeah, indeed, you're yeah. I mean, I've looked at it a little bit for some other reasons, but like, so one thing that we like, you could try to directly compute the matrix elements of the dilatation operator in the Schur basis, and at least in certain, like, and formulas exist, but at least in some of the cases, the formulas were a bit messier. Numerically, implementing these things actually was a little bit, the Schur basis, well, it was just a bit messy for us, because you have to compute things like, what do you call these characters for the,
yeah, no.
And doing these things for very large things ended up being sort of just, yeah. But as you say, maybe for very small cases, it might simplify a lot, and then you might get something quite nice. Yeah, but as I say, in some ways, you kind of expect to get quantum chaos for finite values of n. So it was slightly surprising to find that it kind of vanished for n equals to 2. Yeah, but as I say, I wonder if that's really true for the full theory. Like, I don't actually expect n equal to 4 at n is equal to 2, the rank of the gauge group being 2, to be integrable. I mean, in fact, so I suspect maybe it was something to do with looking at these scalar operators.
Interesting. Any other comments and questions before I close the recording? We can.
Can I ask a question?
Sure, please.
Hi, Tristan.
Oh,
so I was just wondering, like, what's your take on the n equals infinity situation? So I guess when you have infinite coupling, you have this gravity description, and there you have normalization. What happens as you decrease lambda?
Okay, so yeah, I have tried to think about this a little bit. I don't know the answer is probably the best thing to say. But so the first thing is that when you say at large coupling, you also mean at finite temperature. Here,
Well, the thermalization. So I guess that's what you were describing. If you take, let's say, heavy state and try to measure correlators in it, these correlators are going to be the same as correlators in a black hole, so which is a finite temperature state. So basically, this means there is thermalization. The question is, and I suspect at zero coupling there is no thermalization. So the question is there some kind of phase transition?
So let me. So yeah, I mean, what I was looking at, as I say, is sort of, it's the microcanonical ensemble. So effectively, the temperature is infinite. So it's thermalized, but it's at infinite temperature, I guess. Whereas again, when we think about a black hole, we're thinking of like the canonical ensemble, I guess, at some finite temperature. So I'm not quite sure how to connect.
Well, but these two things are the same in large n theories. So if you go to large n theories, then you can do the saddle point analysis, and microcanonical and canonical ensembles are the same at finite temperature. Yeah, at zero temperature. Of course, you have to be on the to consider a finite temperature, you have to be on the sphere, I suppose, if you're talking about conformal field theories. But yeah.
Yeah. So it's certainly true. What you say is that, yeah, there's no like this. Yeah, there's no chaos at zero coupling. So it certainly is a finite coupling thing.
Okay, so these coupling terms were important for you.
Oh no, for sure. So everything I said.
One loop, the fact that you did this correction to the dilatation operator, this one loop correction, was it crucial? Right. Okay.
Yeah, everything is that exactly. So I think adding in the higher loop corrections wouldn't change anything. But, but you need the one loop piece.
Okay, good. So I guess your picture. Well, I don't know if it's a picture, but my guess would be that as soon as you have finite coupling, you immediately have thermalization. But at zero coupling, maybe you don't. That would be my guess, right?
That's no, I think that's right. There is also like some, like the radius of convergence. So when I say I'm talking about the one loop dilatation operator, does that make any sense? Like, you know, so effectively for me, lambda is equal to 0. I mean, if you know what I mean, there's a 0 radius of convergence at finite n. So for me, lambda is 0. So I'm a little bit nervous about, you know, talking about finite values of the coupling, as in I'm not talking about finite values of the coupling.
Yeah, but if you go to infinite n, planar limit.
No, exactly. So at infinite n, then the radius of convergence is finite, absolutely. But then of course I don't have, like for me, if I go to infinite n, I do not have thermalization. And so the one loop dilatation operator at infinite n is integrable. There's no thermalization.
So, yeah, okay. But then, no, at infinite lambda, there is thermalization. So what happens?
Yeah, this is the bit that I'm. Yeah, as I say, I don't know. I mean, so there is something. It's probably some order of limits. So for example, in the perturbative calculation, I first take n infinite. So there's no back reaction of my operators on the geometry. So in this case, there would sort of, I think you would never get a black hole being formed.
Sure, you have to take, to get a black hole, you have to take, you have to take your, you can't even access these operators. Yeah, like, because these are in the regime where your distinction between single trace operators and multi-trace, well, maybe you can, but this is a regime where delta is order n squared. If you want to make a black hole, so
exactly. So I think so I think it's this. So for me, as I say, like when I go to the integrability, I first take n to be infinite, and so then I focus explicitly on single trace operators, and then I won't see any thermalization. And so that's what's happening there.
Then I think it's clear that because with delta being n squared, anything at the n squared, your trace relations are playing a crucial role.
Yeah.
Right. So I think the thing that would be slightly closer to this would be something like what was looked at in this de Mello-Koch thing, where they sort of look at the class of operators where delta is n squared, and then they have some sort of effective Hamiltonian, and then they do see sort of they see scrambling, and that sort of limit of parameters might be as I say, closer,
but I guess still the most natural picture is that as soon as you have some finite coupling, there is some thermalization, but zero coupling, something like this.
No, I think that's true. Yes.
Thanks.
Yeah, sorry, and maybe just to reiterate that exactly. So for me, I sort of need to have n being sort of finite, and then, but as long as as long as I allow mixing between my single trace and multi-trace operators, once I turn on the one loop part, I will get I get quantum chaos, exactly. And I don't get it when it's not there because there's no, yeah. And then once I turn it on, I do, yeah.
Other questions? Anyone want to get a last question in before I stop the recording? We can be less formal then. Okay, I'll stop the recording and we can, well, thanks Tristan again for a fascinating talk. Okay, great.